Good morning, everyone. Today we are going to learn another type of advanced data structure called tree data structure. And this is our lecture overview. We are now in the second last lessons. We are now focusing on the tree data structure. And here is the content of the content for today's lectures. We will see on the introduction to the tree, and we see different type of tree, including tree, binary tree, and binary search tree, or we call BST, and what are the tree operation and how we can access to the element inside the tree, and we'll see on how we can implement it using our C++ language. So first thing first, we will talk about the linear data structure. Actually, that it helps to store and organize our data in our computer in the linear way. So we have learned before, including array data structure, linked list, stack and queue, hash table. Those kind are called linear data structure. It's because they store our data in the sequential way. We can access it sequentially. The way it's stored, they connect to each other from one to another. And when we look in the tree data structure, the data are stored in the hierarchical data. It's like we have a nested level. You will see it in the following slide. However, in the linear data structure, as you can see here, in a way we store the array, the stack, the linked list. Our data are sequentially connected. So here is the comparison between the linear and non-linear data structure. We focus on how our data is stored, how we can access to our data, how we can implement it, the level of nested our data in which it's stored, and memory utilization. In the linear data structure, the data is stored sequentially, while in non-linear data structure, the data are not stored in sorted order. In the how we access to our data, we actually visit it sequentially in linear data structure, but in our non-linear data structure, we need to recursively access to our data. Either we access it from the left or right level, or one level by one level. Talking about the implementations, yes, of course, linear data structure is quite simple comparing to the non-linear data structure. And the way it uses our type of data to store the information, it actually one level only for linear data structure, and we have multi-level elements, which is in the form of hierarchical format in the non-linear data structure. Regarding to the memory utilization, non-linear data perform better. Example of non-linear data structure, we have tree and graph, while linear data structure we have seen before array, linked list, stack, queue, and also hash table. Actually, there are pros and cons either way. In the tree and graph, you can access, you can insert, it's very fast. Okay. Comparing to linear data structure, only hash table that we can access to information quickly. The big O notation is only one, right? Because we use hash function. So now we come to the introduction to the tree. Okay, tree data structure. A tree is a hierarchical data structure defined on a set of elements called node. Okay. So when we learn about linked list, stack, and queue, we have element, right? Each item, each our data is considered as elements. So now we can either call our data in the tree elements or nodes. Okay. Normally, a tree can be an empty or composed of many nodes. And in the top level nodes, we call it root. Root is placed in the top level, while other nodes are called subtree. If you look in the picture on the right here, we have the root, which is called P, right? P is considered as the root of our tree, okay? Because it is in the top level. So by connecting one node to another, we have a line, right? This is called edge. Okay, this is some key term. And normally subtree are those nodes that are beside the root. Okay, you can consider one of the subtree, for example, in the top left here, bottom here. So L here is defined as a parent when we consider only on this subtree. Okay? Subtree not only at the left part end but the bottom. Any connection beside the roots, for example, this one is all so subtree. Okay, subtree. A is considered as its parent. Okay, and for the leaf node, okay, we consider it as those nodes that are in the bottom. Okay, no more further connected nodes. They are called leaf node, or another way, it has no children. Leaf node is called considered as the children when we consider it into the another nodes of its parents, and the node that are connected from the same nodes. I mean, for example, in here we have A and B, which are connected by Q. So these A and B here are called siblings because they have the same parent Q here, right? So if we consider as the subtree here, we have E and F. They are considered as children, or we can say they are siblings. It's okay, but considering on the parents, okay, E, F, G are children to L. But the relationship between E, F, and G, they are siblings. Okay. And considering on the high of the tree, we are taking the low wall. Okay, what is the high of the tree? We can see that how many low wall it has. So in this case, we have how many level? If you can see from this picture, level 1, level 2, level 3, level 4, and level 5. Okay, so we have, if we consider on the height of the tree is 5. Okay. We will take a look in further detail in the following slide on how we access to this information and what is the parents, age, and how we find another term, for example, dip of the tree. So root, they are considered a top element. Children are those nodes they have the same parents, okay, or grandparent or great grandparent, because we have many sub-level. Parent normally they have children. For sibling, they actually have the same parent. And for the leaf, it's considering on the old element that has no children. Normally it in the bottom. Okay. For example, D here is also considered as leaf node because it has no further children. So normally when we implement it, the leaf node normally it points to nil when we implement it as the linked list, because they are in the very last level, right? So for example, on this picture, how many leaves do we have? Okay, and what are they? So the leaf for this tree, we have the nodes A, F, G here. We have B, H, I, and D, right? So together we have 7. 7 of them that I consider the list of our tree. And next, we focus on another term we call age. So what is called age? Age is actually a line which are connected to node together. Yes. For example, in here we have node, right? If we have a tree with the node of n, the total age is n minus 1. And when we focus on the dip of node, okay, dip of node is actually a number of ages from x to root. Okay, we take a look from that node up to the root. Okay, we count the age. This is called dip. For example, if we see that the node A here, what is the dip of node A? So we count the age from this node to root, right? Up to root. So we have this one age and this also another the age. So the dip of A is 2, right? Because there are 2 edges up to the root. And what is the height of nodes? Any node, okay? They are actually the number of edges on the longest part from X, this node, to a leaf. Okay. So down, dip, go down. For example, this node, how many edges it has? We take the longest part. For For example, if we consider on all here, the node all here, what is the height of the all here? We will see go down here on the longest part in longest way, how many edges. So in here we have this one, or either we go left or right. Okay, we have this. So there are 3, right? 3. So just to remark here, normally if we say a height of 3, it's actually the same as depth of a tree. This one we consider on any node, okay, any node. But when we say a tree, okay, depth of a tree, it consider as longest part of the tree. Inside of a tree is the number of elements of the nodes that has in this tree, and for the branch, what we call branch is any part, okay, any way that edge are connected from the root to a leaf. So we go from the root to the down, okay. Either we go to other ways, okay. For example, you can browse through here. This is called a branch, right? Because this is a leaf, right? Okay, and this is called another branch. Another branch here. Okay, we go this way. Okay? So this is some key term that we use in the tree. And let's see this. How many edges does it have? Okay, we can count it, right? Those are lines that are connected to node together. So we have how many? Okay? We can count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? We have 13, okay. And what is the depth of node L? Okay, you can find it through this example. Based on the definition, depth of a node is number of edges from x to root. Okay, so if you want to find the depth of L here, you can count the number of edge from this node L to root, right? So in this case, we have 3. Okay? And how about the height of the node C? Okay, height of node C is normally we find the number of edge on the longest part from this node C into a leaf. Okay, so there are 2, right? Either we go left here or we go this way, okay, to the list of its list. So there are 2 edges. So the next thing, okay, I think you can explore yourself out here. I'm not going through this. You can reflect yourself on how you can find a different relationship of this tree. Okay, what are the size of the tree, deep, sibling, child, subtree, so on and so forth. Okay, next we'll see what are applications that we can use to apply tree. Okay. Tree can be used to apply this applications. For example, to store our data in a hierarchical data file system. For example, our folder and folder are nested. The second one is we can organize our data for quick search, insertion, and deletion. For example, if we use BST, binary search tree, because in binary search tree there's a rule in which we can store our data, whether we store it to the left or to the right of our binary tree. Okay. And we have dictionary. Okay, we can actually apply tree to our dictionary to search our data very fast. Another thing is called network routing algorithm, in what way that we should route it based on the shortest path first or longest path first based on our requirement. So in the tree, either we can store it as a number, a string, or a piece of our data. Consider in the struct for example, you create a struct a student, and each node is considered as a student. You can do that. Okay. Okay, next, what is binary tree? Binary tree, normally it's a kind of tree that has at most 2 children. Okay? Children, those nodes that have the same parent. Okay. Maximum it has only 2. Okay, it cannot have 3 or 4. Okay, it has 0, 1, or 2. Okay, a node can either have a left and or have right child. Okay, so together here you have 1, you have 0, or you have only 1 on the right. Okay, and the leaf node has no left or right child because it is the leaf, right? The leaf, it has only nil because it connects to nil. Okay. As you can see in here, all other leaf also there is a line. Actually, when you implement it, it connects to a nil. Okay. Just like if we implement linked list, the tail is connected to nil, right? And here is the three main types of binary tree. We have some property here: strict, proper, or full binary tree. What are they? And we have complete binary tree and perfect binary tree. So a strict, proper, and full binary tree, it actually refers to binary tree that each node can have either 2 or 0 child. It cannot have only one child. Okay? Either it has no child, it means that they are leaf, right? We cannot have only one line here because this is not allowed in the strict and proper full binary tree. Okay? It's just a property. And for the complete binary tree, it is a kind of binary tree that in which every level except the last, it actually completely filled and all nodes are far as left as possible. So what does this mean is that except the last here, okay, as far as less possible, it must be completely filled. It means that it's a kind of strict and full, right? It must have 2 child. Okay. So these are considered as the complete binary tree because except the last, we have our data here, right? As you can see that each of them are considered as the full binary tree. It has left child and right child. So next is perfect binary tree. They are considered that all level are completely filled and balanced. It means that on the left and on the right they must have the same, right? Okay, the same here. For example, if we don't have this one, it cannot consider as the perfect binary tree because they are not balanced, right? Balanced means that on the left and on the right, the level inside here they are the same, okay? And must be completely filled. It's just like a full binary tree and plus every level they are the same. Okay,